Hi, I'm Tom. How you doing? Please bear with me if I fumble the technology here. So I'm going to talk about machine learning. I've done lots of stuff in the past. I do lots of stuff today. I spend a lot of my time worrying about how to engage and neutralize adversaries that have breached a system. That's what I'm doing lately. I've done a lot of machine learning stuff in the past. I've looked at how we can use machine learning today. I got involved with neural nets back in the 1980s. By that time, machine learning was pretty much old school. It actually got started back in the 1950s, I think, and it was studied quite a bit. What really made it take off were the speed of CPUs and how much storage we had, the storage devices. And so now we can solve systems of equations much faster, and we have much more data that we can use to analyze. However, it's not a panacea. As you've seen some things in the news recently, machine learning things can break down in interesting ways, sometimes in ways we don't like. So there's a lot of stuff here. It's going to be kind of superficial. I'm trying not to make this a computer science talk or a mathematics talk. I want to focus on the security aspects. Specifically, why do we get false alarms? What I'm talking about for machine learning also generalizes to other types of systems that detect things, classifiers in general. So with that, the things that you should be taking away from this are, if you've never used machine learning before, what is it, how does it work, where these false positive things come from, what does it involve? And for people who actually use machine learning, either in production or they're just toying with it, to give you some things to think about in terms of feature spaces, what should I train it with, how should I define what it's operating on, etc. So there's three parts to this talk. This is going to be a kind of an experimental talk. We're going to see how it goes. The first part, I'm going to give a very general introduction to machine learning. And specifically, I'm going to be looking at artificial neural nets, and even more specifically, one specific kind of artificial neural net. The second part of this talk is the steampunk apparatus for machine learning. This is my pneumatic neural network, and I've got one set up right here. I don't know if you can, people in the back might not be able to see it. What I want to do is when I start the second part, I want to invite whoever's brave enough to come up to the table up here to play with it. There's a bunch of knobs up here. So if we go back to that first page, you see that picture, that's what's up here now. And it's actually a physical implementation of a neural net. So the thing that you would use to train and classify things, you can do with this. And we'll talk about the problems that you can solve with it. So the first thing, I'm sorry. And the third part, we're going to solve some real problems with it. So we're going to say, what can this thing solve? What can it not solve? And why can't it solve it? And what would we have to do to make it so it could solve the problems that we've got? So machine learning, I'm going to go kind of fast. So we have a lot of security applications for machine learning. For example, a bunch of code, is it malicious? The login times of users, do they look unusual? The patterns of our network, do they look okay for a Tuesday afternoon? Is the data flow look normal or not? Does it look like we're exfiltrating something? Does it look like a malicious payload or some unauthorized payload might have just been downloaded? Here's an example of a problem that many of you might have faced personally. You're looking at a piece of code, maybe it's a binary dump of something, and you need to know, what is this? Is it malicious or not? Is this just some core dump that ended up on the system, or is there some kind of malicious payload hiding in this? And I'll give you a spoiler here, this is not malicious. This is actually a binary dump of a small program that was not malicious. You might have a bunch of log files. Here are the timestamps. There's a bunch of stuff in them. Did anything unusual happen during this time? Were there any intrusions? These are hard problems. They're very hard problems. They take a person a long time to figure out. So let's use machine learning and see if we can solve these kinds of problems. So what does that entail? So machine learning is basically, you've got a bunch of inputs, and you feed it to your machine learning system or your neural network or whatever you want to call it, your AI system, and it's going to spit out a bunch of output. Well, that's okay, but we want the right output. So what we're going to do is we're going to give it a bunch of input. Now we're going to give it a bunch of output, and we're going to say this input matches that output. And that's the training phase of machine learning. Okay? And the third part there is you're not probably going to get it perfect, so let's just get it close enough. And that's what we're trying to do with it. There's some buzzwords here on how you can put together neural nets, what they're made of. It's not that important right now. The most important thing to take away is that there's not a right way to do it. Someone might preach and say, machine learning is done this way, or a neural net is done that way, and there's so many different ways that you can put these things together. There's so many different types of equations you can use, so many different types of training algorithms. Here's an example of a neural net. This is a simple one. So what you're looking at, the circles there are, we'll call them neurons, okay, and they hold a state. Is it turned on or is it turned off? And the ones on the far left, those are the inputs, okay? So it may be our malicious code. Now you're seeing a simple one, and I'm going to show you in another slide what it looks like when it gets more complex. But here are my inputs. And the inputs define your feature space. These are the things that you're actually measuring and feeding into your machine learning system. And then you've got another layer where they're feeding in, and those features or inputs on the left are feeding into another layer of neurons, and those become features in their own right. Not necessarily features that you can understand what they are, but they're features. And those features will feed into the final output. And the final output will give you something like a yes or a no, or it's blue or it's red, for example. And the more layers you have here, that's what deep learning is. Deep learning is when you have many layers of neurons. I see that the slides are getting misaligned here. Oh, please don't. There we go. All right. Okay, so the topology, how those neurons are wired together, this is part art, part science, part black magic, trying to figure out how many neurons do I have, how are they linked together, what kinds of inputs am I going to use. So here are some examples of neural nets that have been used. The one in the bottom right was out of a textbook, just demonstrating neural nets and machine learning. The one in the upper right was out of I believe it was a geology paper, and the geologist had used this neural net to train a machine learning system to recognize certain types of soil. And then the one on the far left was a neural net that was designed to recognize Pascal programs. I don't know how many programmers there are, but Pascal is a programming language. Usually not used. Usually, it was used many years ago, more so. Let's see. And references if you're interested in that stuff when you get the slides. So machine learning is going to learn these patterns. We give it the input. We tell it to train itself, to tune the knobs. And in the second part, you're going to see that there's real knobs involved here in our physical implementation. And then it's going to give you the output, right? And we hope that the patterns don't change, right? We hope that if this happens, then that happens, and it's always going to be that way. And if it doesn't, then that means something's broken, right? Something, for example, a malicious intrusion. So, breaking the law. So it learns the rules, or the patterns, right? And then who breaks the rules? The bad guys, the adversaries. And so that's the hope. The hope is that we're going to have this this machine learning system that learns how our system behaves on a regular basis. It learns what's normal, and then when we see something that's abnormal, hey, it must be a bad guy, right? Because the rules have been broken. Except, well, hold on, there's other things that actually break the rules, and now we're getting our first indication of maybe something is wrong with this way of thinking, of taking a machine learning system and using it for the end-all, be-all of our security. Because there are outages, there are upgrades, policy changes, business policy changes, there's employee turnover. And any time one of these things change, they change the relationship between the inputs and the outputs. The inputs are things like the stuff in our log files, the binaries that we're seeing on the file system. And the outputs are our judgment as to whether it's okay or not, whether it's normal or not, whether this is malicious or not, whether it's acceptable use or not. So now I'm going to go into the second part. So that's a general overview of machine learning. Now, it's deep stuff, and there's a lot of math involved, and I didn't think that most people, they'll kind of go to sleep if you go into all the math. So I thought, hey, this is B-Side San Francisco, and the theme here this year is steampunk. And I don't have a steampunk outfit. I'm sorry. I see a couple people have got them. But the best thing I can do is I can actually build an apparatus that uses tubes. I would actually like to use a little steam engine, a pneumatic steam engine, except I came in an airplane, and I don't think they'd let it on the airplane. So right now, I'm going to invite however many volunteers are brave enough to come up to that table over there and actually play with this apparatus, which is plugged in and running right now. Are there any volunteers? Anyone bold? All right. Just right up front there, right up front. So you guys are going to see this thing firsthand. Everyone else is just going to see these fuzzy pictures on the screen. So that picture is, so I'm going to go through these slides and just watch as I go along, and you guys can fiddle with the knobs, and you're going to see what all these things are for. So we have, in our apparatus, we have an air pump. So we need a source of energy. And in this case, it's an aquarium air pump. It's an 80-gallon aquarium air pump, and it's got a little dial that adjusts how much air is flowing. It's plugged in, so that should be live. We've got 4-way metal gang valves, 3 of them in this case. A gang valve for an aquarium system is 1 tube goes in and 4 come out, and it's got 4 little valves. And you'll see a schematic diagram here in a moment. And there's tubing, so we're not using wires. This is all air. It would be steam if we could, but I don't think that would be practical. And then we have a comparator, which was custom made by my son out of Legos. So the challenge here is that we've got 2 tubes at the end of our system, and I'll show you some diagrams here. 2 tubes, and each one's blowing air, and we need to know which one is blowing more air than the other one, right? And so there's a Lego device up here. It's little Legos, and then there's a little plastic BB in the middle, a plastic ball, and one tube is blowing it in one direction, the other tube's blowing it in the other direction, and then there's a bias. So you guys see that thing underneath? You can adjust it to adjust the slope, which will bring the little ball down to one side, right? And so the ball would naturally fall down to 0 unless one tube blows it up to 1. Now let's look at some schematics here. So what we're modeling here with this physical model is a single neuron, really, wow. So the one on the right there, the output neuron, that's the neuron that we're modeling. And then there's 4 inputs. And those inputs aren't really neurons. They're not accepting anything. We're just turning them on or off. And in this case, what we're doing is we're modeling a 4-bit number. So we're not going to analyze any malicious code with this pneumatic neural network, but there are some interesting problems that we can do with it that involve 4-bit inputs. And basically what it's doing is those 4 inputs, it's fusing them together, right? There's an equation behind this, but if you look at it, it's actually a physical commingling of the air inputs. So here's a gang valve. So the blue circles are what a hose connects to, an air hose. And the little yellow things, I use those to represent valves that you can turn on or off. And you can actually put them in halfway states also. So in a neural net, in an artificial neural net, these would be considered the weights. So a neuron is tied to a neuron, and then there's a weight. So this neuron has so much of an impact on another one. And this is a more elaborate diagram of what these guys are playing with right now on the table. So we've got the air pump going to the one on the left. The 4 valves on the left represent our input, our 4-bit number, right? So you turn them on or off. And they're actually labeled. So if you look at that in terms of binary, you have a bit for 8, you have a bit for 4, you have a bit for 2, and you have a bit for 1. There are 4 tubes coming out of there. Now, in theory, well, not, okay, so really what I should have done is put little T-splitters on those and then have 4, each one of those go to the top and each one go to the bottom. But that's more expensive and it's more stuff to carry in my backpack. And so instead I just had 4 hoses, and then you can disconnect them and reconnect them to whichever one you want. And you'll see that one of those splitters is going to represent a positive bias, and one of those splitters is going to represent a negative bias. Another way to put this is one of those splitters on the right will push the ball in one direction, and the other one will push the ball in the other direction. And the valves on the splitters on the right, just before the green triangle, which is our comparator, each of those represents a weight. So how much impact does its input have on the output? And then the comparator here, again, it's a little Lego thing. Maybe afterwards y'all can come up and look, and it blows a ball in one direction or the other. And so now we're going to take this, and these guys are going to solve some problems with it, right? So we've got 4-bit inputs. So here are 3 interesting problems to solve. One, can you make it so that the ball will tell you whether the number is even or odd? That's one challenge. Another challenge is, can you make it so that the ball will tell you whether the number is greater than 3? And then the final challenge is can you make it so the ball will tell you whether the number is prime or not. So a prime number cannot be divided by anything other than 1 in itself. And the first prime number is 2. So 0 and 1 technically are not prime. Now we're going to look at the answers here while they fiddle with it. So with this simple neural network, this pneumatic neural network that we've built, the first 2 problems give us what are called linearly separable data, right? So let's say you're going to ask, our question that we're trying to answer is, who can be heard through the microphone, okay? And so it's those guys or me, so we're not gonna let them talk. So those guys are me, right? So we can draw a line right here, right there, and we can say, everyone on that side of the line cannot be heard through the microphone, but anyone on this side of the line can be heard on the microphone. Linearly separable. So the even-odd problem is linearly separable. We can divide these up by looking at the 1 bit and say, well, if the 1 bit is on, then it's odd. If the 1 bit is off, then it's even, right? And so you can very neatly divide your data into 2 piles. And that's what this thing can do. And there's a solution on the next slide, and we'll see that. And greater than 3 is also linearly separable with this device. So what we do is we look at the first 2 bits, and we say if either one of those first 2 bits are on, if they're set, then the number is greater than 3. If both of them are turned off, then the number is not greater than 3. And so here's a solution for even or odd. So you look at the bits, and you look at that 1 bit, and you're going to push the ball in one direction or the other, and we're going to push it in the positive direction, and that's uphill. Think of +1 as going uphill, and here it's quite literally, it blows it up the hill with the pipe or the tube, and the others have no weights. So we actually disconnect those tubes. They don't do anything. All we care about is that 1 bit. And so if it goes, it's going to blow uphill, and if it doesn't, then there's a bias, it's a ramp, and the ball rolls downhill. It's very simple. Simple problem, but remember what we're trying to solve are hard problems, like is this malicious code? Were the login patterns on Monday, were they normal or not? So let's make it a little bit harder and see what happens. Is it greater than 3? Again, it's easy to make the data linearly separable. We put +1 weights on the 4 and the 8 bits. If either one of those is set, it's going to blow the ball uphill. If neither one is set, it's going to naturally roll downhill because we have a little ramp and the ball rolls downhill. And then there's the hard problem. So if you look at the prime numbers, if you look at the numbers 0 through 15 and you say which ones are prime, they're divided up here with the bit patterns. And so now this is kind of like a forensics challenge. We're saying, here's what we're seeing. How can we decide whether it's good or bad? How can we decide whether we want the ball to roll uphill or downhill? And I left out 0 and 1. I called them undefined so I can illustrate a point in the next slide about false positives. So does anyone have any ideas on how you might separate, or these guys maybe, do you guys have any ideas on how you would adjust the knobs to tell you if it's prime or not? Right. Oh, okay. They're working on the binary. So he's taking a look at the slide. Okay. So I'm going to skip ahead. So here is a possible solution. The first thing that you should notice is that it's not a simple neural net anymore. I cheated. I added more layers. Okay. We could probably do it in 2 layers, but I'm showing it in 3 layers right now. So the way to, or one way to solve this, because there's never a right way to do this, but one way to solve this is to train, and when I say train, these guys are training the system right now. So if you ever wonder what a machine learning system is doing when you're training it, it's literally doing this. It's going through and experimenting and going back up and saying, I turn the knob and the ball goes this way or that way, it didn't work, so I need to adjust it. It's trying to find local minima and maxima for each of these weights. So we can train these intermediate layer of neurons and have the top one decide, is it 15 or not? That's a pretty easy one to figure out. We can say, is it 9 or not? That's fairly straightforward. We can say, is it odd or not? Right? We've already done an even odd. We can say, is it 2? And if you train that middle layer like that, then you can have a neural network that will tell you whether that 4-bit number is prime or not. Except, there's going to be an exception, and I believe it's either a 0, 1, 1 is going to be a false positive, right? So what we can do with this is we can say, look, if the number is odd and it's not 2, and it's not 9, well, I'm sorry, if the number's odd and it's not 9 and it's not 15, then it must be prime, except 1 is not prime. So 1 would be a false positive in this. And so why do we have this false positive? Well, the first thing to note is that we had to pull out extra features there. And if we draw a line and we talk about linear separability, we're talking about linear separability in a single dimension, right? It's over there, it's over here. Here we're talking about something that's linearly separable in 4 dimensions, right? So we've got to check to see if it's 15, so that's 1 dimension. We've got to check to see if it's 9 or not, that's another dimension. You've got to check to see if it's odd or not, and then you've got to check to see if it's 2 or not. And then if we want to be really good about it, we want to check to see if it's 1 or not. That would be 5 dimensions if we added another, or we could pick that up in the next layer of neurons. So as our data become more complex and harder to organize, we have to add extra dimensions. We have to add extra layers to our neural network, which implies us adding additional dimensions to our problem space. So now we've got to think in 4 dimensions, or 5 dimensions, or 1,000 dimensions. So you might hear about people training machine learning systems using thousands of different inputs simultaneously. That's actually processing a system that's working in thousands of dimensions, something that's very difficult to geometrically imagine. And each of those intermediate layers represents features. And features that you might not have thought about, but the machine found through essentially trial and error. There was something in the news recently about, I think it was playing Qbert, the video game, and it found a solution to the Qbert video game where it could rack up the score, and it did so by exploiting a bug in the Qbert program, in the MAME implementation of Qbert that nobody knew about, but it found it because it was just randomly kind of going around and exploring, and it found it. So here's our 3 main points here. Higher dimensional problems, they require more layers of neurons, and that's where this notion of deep learning comes from. More layers require more data for training, and too many layers means we can never train enough. And that's a little bit too much to explain in a short talk, but the gist of it is that when you have higher dimensional space, you have more possible places where the data could land as outliers. And if you don't have sufficient training data, you're never able to train the system on all those possible outliers. And why is that important? If we think back to the who breaks the rules slide, right? We think it's the bad guys, but wait, there's outages and stuff. And we're trying to train our system to tell us if Monday was normal or not. Out of any given year, 5 minutes left? Oh, sorry. Out of any given year, well, there's only 52 Mondays. Right? So how much can we train it? If we're training it to recognize images of dogs or cat videos, that's one thing, because there's a lot of those, and there's no shortage, and people will just keep making them. But if it's for your organization, and you're trying to figure out, are the machines working correctly on this Monday or not, there's not much data that you have to train it on. And so in this high dimensional space, that creates a problem. And so where are false positives coming from? There's 2 problems. Either we don't have enough layers in our artificial neural network, so we can't adequately separate the data, and some data are going to land on the wrong side of this line or this hyperplane, or we've got so many layers that we can't have enough we cannot find enough data to train it, right? We may get faster computers, but if there's only so many Mondays, then we're stuck with there. So the takeaway here is sometimes machine learning works, but the system will be fragile at best when an adversary is involved, because while it's great for the natural sciences, it's great for problems where your data sets are fairly predictable, fairly stable. It doesn't work well when your environment is changing on a regular basis, like it is in a business, or when you have an adversary who's actually injecting data into your system, trying to deliberately break your system. Oh, he's still tinkering. Cool. And that's all I've got. Did I run over? Okay. Thank you.